Hi everyone, I'm Hanyu. Today, we'd like to talk about two papers, Pigs to Pigs and Cycle Gain. Both of them are very influential deep learning works published last year, and I have sufficient reasons to assume that most of you have heard them. I will start with the common goal of them. Then, Now and Jiayong will introduce their method in details. Finally, I will make some comparisons and contrasts between them. Well, before going much further, let's talk about creating art with deep learning. Art has long been considered a quintessence of human intelligence. However, recently benefited from the advance in artificial intelligence, and especially deep learning. We have AI techniques that can somehow create art now, at least with limited human help. Take a look at these fantastic images. All of them are generated automatically by a photo editing app called Prisma, with some featureless photos as inputs. How does it do that? The answer is neural image translation. What is that? Basically, the terminology image translation refers to translate an image to another one. So neural image translation just means achieving this goal using neural networks. Let's see a simple example. Here are three images. The left is just a street view of a European city. It contains a river and some European architectures. So let's call it Image Europe. It's very ordinary, and you may not want to stare at it for more than 3 seconds. However, we should admit that it's like the most common photos that we can take. Now look at the middle one. Without any doubt, it's a starry night, a celebrated work by Van Gogh. It is famous for its fascinating color style. Many people try to simulate it in their own words. Finally, the last one. It is the most interesting one. Clearly, it contains a still river and some architectures, which are same as the image Europe's. However, it is definitely in the Starry Night color style. In fact, it is a style transferred image using image Europe's content and Starry Night's style. Given a featureless image, Van Gogh's style transfer neural networks can translate it to a style transferred result. Let's see how Pigs2Pigs and Cycle Gain can achieve this goal.
Thank you, Hanyu. Now, let's start with the basic. A basic generalized adversarial neural network, or GAN, has two neural networks as its components, discriminator and a generator. The generator keeps generating false images from a random noise and tries to fool the discriminator, which tries to tell apart the real image from the fake image. In basic GAN, it generates image from a random noise, but this is not very useful. Often, we need more than generating a random image that looks realistic. In case of conditional GAN, we have a label that feeds into the both discriminator and the generator, hence conditional. Now, the discriminator has to decide whether a given image is fake or not, and whether the condition given is met in the image. The loss below here seems pretty complicated, but it's actually very intuitive. The expectation of log is equivalent to the cross entropy, and G is right now trying to fool the discriminator, meaning higher entropy from discriminator, hence argmax over D. The discriminator is then trying to outsmart the generator, meaning it is trying to lower its entropy, hence argmin over G. Note the conditional GAN uses basically the same formula, except now we have the label in the parameter. Now let's talk about pixel to pixel. In case of pixel to pixel, the goal of this neural network is to translate one image to another image. It may not be clear, so here's an example. So we can change a day image to a night image as shown in the PowerPoint. In order to achieve this task, pixel to pixel uses conditional GAN. Now the inputs Now the inputs are fed into both discriminator and the generator. The discriminator now has to tell apart whether an image is fake or not, and the image is close to the original image. Pixel to pixel does not deploy random noise because in the original experiment it seems like the neural network learned to ignore the noise, so it always generates deterministic images. It uses dropout, but the outcome is not very stochastic. Adding randomness is up to the future research. Now let's talk about the structure of the discriminator and the generator of pixel to pixel. Traditionally, GAN uses an autoencoder shaped generator. The kernel, the bottleneck of the neural network, represents the minimum possible information to generate the image. However, in case of image translation, because the input image and the output image should match as close as possible, folding an image to a kernel risks risks generating a low resolution image. Therefore, in pixel, we use UNet, which provides skip connections between nth layer and n-ith layer, so that the value of the original image can still affect the output image. As you can see from the image on the right, in case of loss, they have this regular conditional GAN loss we saw before, and L1 loss. They have this L1 loss because they want to generate the image that is as close as possible to the original image pixel-wise. For the discriminator, pixel to pixel uses the patch GAN. It basically scans n by n pixels of patches from the original image and tries to tell whether the image is fake or not. It does scanning for every pixel, then averages the output and return it. In physical term, it roughly means it's evaluating the loss of the texture and the style of the patch. The advantage of having this patch is that this operator can be applied to an arbitrarily large image with small cost because it has fewer parameters. The patching also works as a Markovian random field. For both network, they used convolution layer, batch normalization layer, and ReLU layer as the one basic unit. So 3 layers packaged into one layer. This is an example of pixel to pixel using different size of patch size for discriminator. As you can see, the size of the patch does not have to be as big as the original image. 70 by 70 is already generating a very sharp image, while 286 by 286 produces a bit blurry image than 70 by 70. So this is the example generated from pixel to pixel using different settings for the generator. In case of the autoencoder model, it produces the blurry image that you can tell it is fake, which is often the problem of autoencoder. With UNet, however, it generates an image that is really close to the real image and very sharp. So this is another example of pixel to pixel. Now it shows how different losses shape the image. With only L1, the image is very blurry, like the one we saw in autoencoder. With CGAN only, the image looks realistic, but kind of surreal and awkward. But still, it achieves very high accuracy, and it can be viewed as generating its own discrete labels. With both L1 and CGAN, you can see that it is generating images that are very close to real image without any awkwardness. The final note, note that pixel to pixel only works in one way, not in the other way, and it is very deterministic.
In the pixel-to-pixel paper, we introduced the general-purpose solution to image-to-image translation problem. Now, I'm going to introduce another approach to the image translating task, which is called CircleGAN. Instead of learning translate an image to image like pixel-to-pixel approach, the CircleGAN is learning to translate an image from a source domain to a target domain. Like pictures I showed here, it can change the style of the image, like from the summer image to the winter image, and also change the photos to the drawings, and also change the photos between different animals. Here is a problem. If we want to train a model can transfer an image between daytime and nighttime, we need to find a large number of daytime and nighttime photos of the same location. This task is too complex. Therefore, CircleGAN is using unpaired data instead of paired data to train the model. We are given one set of image in domain X and the different sets in domain Y. In our case, the X domain will contain all the daytime image, and in the Y domain, it will contain all the nighttime image. And we don't have information about the relationship between the image in domain X and in domain Y. We may train mapping a generator such that the output of the generator is indistinguishable from images in domain Y. By doing this, we also need to train an adversary discriminator to classify the output of model apart from Y. Generally, the optimal generator we trained will translate the domain X to output domain distribute identically to Y. However, this will lead to another problem, which is called model collapse. In brief, model collapse occurs when the generator learns to fool the discriminator by concentrating the output distribution to one side of the data distribution. When the discriminator realizes the generator is cheating, the generator will change their strategy. It will concentrate to another side of the data distribution. It will act like Tom and Jerry, chasing each other. Generator will never learn all models in the data distribution. Like the example I showed here, the generator will map most of the input images to the same output images. Like the cartoon image at here, you can see the image in the red box is exactly the same. And also the room image at here, you can see some room image repeat more often than others. To solve this problem, we will add more structure to our objective, which is circle consistency. It added inverse mapping to strengthen the transformation. The whole meaning behind the circle consistency is that after transform the image from the domain X to domain Y, it should be able to convert it back to the X domain. Therefore, the model will learn two mappings, G and F. G is from the X domain to the Y domain. The F is mapping from the Y domain to X domain. It will solve the modal collapse because when mapping back to the source domain from the same image, the model will complain and update that. With large enough capacity, a network can map the same set of the input image to any random permutation of images in the target domain, where any of learned mapping can induce an output distribution that matches the target distribution. Thus, adversary laws alone cannot guarantee that the learned function can map an individual input from X domain to DZ output in Y domain. Therefore, the difference between the unadorned image and the recycled image will also be considered in the loss function. The loss function for the circle GAN has two parts. The first part is adversarial loss for mapping G and mapping F, and also the circle consistency loss for both mapping. The paper analyzed the effect of each loss, and it shows that none of these losses is dispensable. As you can see here, the paper tests on different combination of losses, different variants of their methods for mapping labels to photos trained on cityscapes. From left to right, the first column is input images. The second column is using the circle consistency loss alone, and the third column it is using GAN loss alone. As you may recall here, the circle consistency loss has two parts, forward and backward. Next, they use a model with GAN loss plus forward circle consistency loss and a GAN loss plus backward circle consistency loss, and also trained on the circle GAN. The last column is a ground truth label. As you can see here, both a model using circle consistency loss alone and a GAN loss plus backward circle consistency loss fail to produce images similar to the target domain. And the model using GAN loss alone and a GAN loss plus forward consistency loss suffer from the model collapse, which is produces very similar images no matter what the input images you feed the model. The author of the paper also used some techniques to improve the model performance in the implementation. In order to enhance the model's stability, they replaced the GAN loss with least square loss, and the results show that it did generate higher quality results. In addition, in order to reduce model collapse, they update the discriminators using a history of generated images rather than the ones produced by the latest generators. To be exact, they keep an image buffer that stores 50 previously created images. Here is some fancy results from the circle GAN model. In the first two columns, it transfers images between horse and zebra. In the last two columns, it transfers between summer and winter images. It is very powerful. It can accurately locate atoms in the image and change it based on what it learned. Personally, I can tell those generated pictures are come from computer. Those are very similar to the art I have ever seen. In conclusion, circle GAN has a good future in the image manipulating and generating task. Making use of unpaired data is pioneering. It makes circle GAN more practical because it is much easier to find the data. At the same time, I would like to use word dangerous to describe the circle again. Our naked eye will not recognize real or fake anymore.
Well, now I'd like to talk about similarities and differences between cycle-gain and pix-to-pix. In fact, from the functional perspective, there is no significant difference between the trained models of cycle-gain and pix-to-pix. Both of them are simply translation functions that translate one image to another. For example, in the right picture, we show two representative tasks. The top one is a translation between semantic segmentation results and photos. Semantic segmentation results assign labels to different parts of a photo to tell others what parts of windows, walls, and so on. It shows the possibility to employ image translation as an image semantic segmentation method. The bottom one is the translation between shoes and edges. Shoe images are just photos of shoes, while edge images are some sketches of shoes. Although shoes to edge seems trivial, many edge detection algorithms can also do it well. The edge to shoes is quite impressive. Maybe one day artists only need to draw sketches and then AI can help colorize them. Some of these tasks may seem difficult. Nevertheless, given sufficient paired training data, both cycle-gain and pix-to-pix can do it well. However, the training procedure of pix-to-pix and cycle-gain are quite different. As Now and Jiayong mentioned, pix-to-pix is trained using paired images, while cycle-gain is trained using unpaired images. The lack of corresponding ground truth makes the learning of cycle-gain much harder than those of pix-to-pix. And that's also why cycle-gain's architecture is more complex and it needs a cycle consistency loss. Moreover, although cycle-gain has tried its best, given paired data, cycle-gain cannot beat pix-to-pix in performance, because cycle-gain can only utilize training data in a paired manner, thus receive less information compared to pix-to-pix. Now let's look at an example. Here we show some results from the cycle-gain paper. It is translation results between aerial photos and maps on Google Maps. It's a very meaningful task because all map providers hold intensive demand in it. The world is rapidly changing, so map providers need to update their maps. However, drawing maps manually is very tedious and costs a lot. If they can generate high-quality maps directly from aerial photos, their productivity will increase significantly. Fortunately, they have cycle-gain and pix-to-pix. Clearly, no matter in which direction, pix-to-pix results are more similar to the ground truth. Cycle-gain's results are darker, and their texture are a little fuzzy. Therefore, if we have sufficient paired training data, just use pix-to-pix. It's faster and performs better. So, is Cyclogen less useful than Pix2Pix? The answer is definitely no. On the contrary, Cyclogen holds promise for a wider range of applications. We should know that the advantages of Pix2Pix are all based on the ideal situation. That is, we have sufficient paired training data. However, in the real world, generating paired training data is very expensive, thus very rare. Therefore, in most applications, we can only train a cyclogen. For example, in this style transfer test shown on the side, we hope to transfer an image's artistic style to other artists. However, other artists never paint certain contents in their own style, thus we can hardly obtain paired training data to train a Pix2Pix model. We should admit that if someone is super rich, he or she can hire a lot of professional artists to imitate certain artists' style. But you know, most companies do not have such crazy funding. But using Cyclogen, we can easily achieve this goal, to translate any image to Van Gogh's style or Monet's style. So we can say Cyclogen makes perfect sense.